whereas plus 2 would move it 2 to the left. Okay? Yeah. So, again, when you get to college algebra, you're like, oh, yeah. Okay, that makes sense. So just plant those seeds. Okay? But you can see how these equations start to talk to you. If you know the family you're in, the absolute value family, and then you start to see, well, what things are added or subtracted where in the equation, you can start to visualize the equation. You can start to visualize the graph of it. It will speak to you. Okay? If we look at our, what did we have? We had y equals 2x minus 3. Oh, you know what? Hold on. Because I realized, just in case you read this, I wrote this down wrong. This makes a huge difference. I'm realizing this is not it, obviously. Okay. This is y. I just flipped it over. Y equals 2x in a minus 3. That minus 3 is outside the bars.
Yeah, that's how it goes.
Yeah, okay, good. Speak up. Hey, I make careless mistakes. I do. Speak up. You know, absolutely. Let me know. It happens. Maybe I'm just testing you, but sometimes not. Right, so that's 2x absolute value of minus 3. So what do you think this minus 3 is going to do to this graph? Drop it 3. What do you think that coefficient of 2 is going to do?
It's going to expand.
Mm-hmm. Right. Yeah. Adding or subtracting things shifts. Multiplying, expands or contracts. Right. Now, you think, oh, 2, that's going to make it bigger, right? Let's take a look. So, before I put in that one, let me just put in the 2x before I add the negative 3. And what happened? It's the red one. Yeah. Well, it's funny. It's like you think 2, that should make it bigger. It actually is stretching it. What it did is it made the graph get bigger faster. Okay? So it actually stretched it up faster, which makes it look skinnier. Okay? So you put a coefficient on it. If it's a bigger coefficient than 1, then it stretches it up faster, which makes it look skinny. If I put in y, and one problem with Desmos is you can't enter fractions. I hope they're going to change that soon because it'll make it easy. But so I'll just put in 0.5 for 1/2. 0.5 x. There's the blue one, and it made it. Yeah. So a coefficient of less than 1 means it didn't grow as fast. So it makes it look more squat and wide. Now, let's put this one in here. And so this was the one we had minus 3. Yeah, 2x, absolute value of 2x minus 3. So there we go. We've got the 2x, so it's skinnier than the parent graph. The black one is the parent graph. And then this red one is the parent graph, but with 2x. So it's skinnier than the parent. And the blue one is just like the red one, skinnier than the parent, but it is dropped by 3. And you can even have multiple things to put in here. Let's say plus 4. So that both did, it looks a little different. It doesn't look like it moved 4 over here, but that's also because it was made skinnier. Okay? So, like I said, that's when you get into algebra and you say, oh, how do I graph this just by looking at those numbers? And 3 things are happening here. It shifted up or down, it shifted left or right, and it's also contracted or expanded. Okay? So, the same things are happening with a line. They're just not necessarily as obvious as that, but the nice thing about, they are obvious once you get used to looking at it, but the nice thing about a line is there's 2 basic properties of a line that you want to be able to recognize. You want to be recognized whether it's plus or minus something on the end, just like with the absolute value, which means that line is going to be shifted up or down. Okay. And what's the other thing that makes a line unique, different from another line?
If it's positive or negative.
Positive or negative what?
Like if the slope is negative or if the slope is positive.
Right. And if it's a positive slope, what kind of line is it?
Just straight up.
Yeah, upward, like you're walking up a hill. If it's a negative slope, it is a downward line. And what if it's a really big slope? Is it regardless of whether it's positive or negative, if its absolute value is really big, greater than 1, is it steep or shallow? Yeah, the bigger the slope, the steep, bigger the absolute value of the slope, the steeper the line. If you got a fractional slope less than 1, yeah, pretty shallow, yeah. So the slope, you're defined by where the line is on the y, where it crosses the y-axis, and how steep or shallow it is, and also whether it's, its slope, which tells you whether it's steep or shallow and upward or downward. Okay? So those two pieces of information allow you to graph, to visualize a line and to graph it. Okay? And if you expand it just a little bit from any equation, any linear equation that you want to graph, you can easily find both intercepts, x-intercept and y-intercept. How many points do you need to make a line?
2.
2. So if you find the two intercepts, one x and one y, you have a line. And the other thing is you can find the slope. So if you have 1 point and a slope, you plot the point, count off the slope, you get a second point, you got a line. Or you plot 2 points, connect the dots, you have a line. Okay? And every linear equation is going to talk to you. It's going to tell you all of that information. Okay? You just need to learn its language, how it's speaking to you. Okay? So we're going to move away from absolute value and now focus in on the linear equations. And we're going to specifically define them as functions. If you hear me use that word interchangeably, linear equations are linear functions. Your linear equations are functions. We'll define what that means on Thursday. But they are functions with one exception we'll look at. The one kind of line that's not a function, but most of them are. Okay, let's switch gears here. Any questions? Okay, like I said, I'll post a link to this Desmos. It's fun to play with. And you can really see how different things you enter will change the nature of the line or whatever you're graphing. Okay. Still recording? Okay. Okay. Sure. I just stayed. Sorry, I just want to make sure I stay organized here so when I scan in notes and things, I'm not mixed up. All right. Yeah, okay, great. All right. Okay, so let's take, now we're focusing in very much on linear now, though you're going to see in the homework come up, sometimes nonlinear equations will come up. Okay? And a lot of the principles are the same, but most of our attention is going to be on the linear moving forward. So let's go ahead and solve basic linear one variable, single variable equation, 2x minus 3 equals 5. Solve for x. Single variable linear specifically. What makes this linear?
Yeah, there is no, it's just a formula. There's no absolute value.
And no, what did you say too? So no absolute value, no. Yeah, no, but also besides absolute value, what else about the x? Yeah.
It's just alone.
Yeah. Yeah, no exponents, no absolute value, no radical signs. Yeah, a nice clean x, or if it's the related to variable, a nice clean x and a clean y. So that makes it linear. If you got anything else going on with the x, it belongs to a different family. Okay. So of course I'm going to add 3 to both sides and divide both sides by 2. And what you have here is a solution set for, and as I'm going to contrast, I'm going to make very, very clear algebraically about this because I'm going to contrast it. This is 1. Of course, it's 1 because it's linear. Okay. Linear has one solution. That is based on, as we'll get into this, we get in more into polynomials and other things, that's based on because what is the exponent on 1? I said it was clean, it doesn't have an exponent, but it actually does. What is the exponent on x?
B, just 1.
Yeah, it's 1, yeah. Which means that exponent means that's the degree. The highest exponent in this is a 1. That's actually more technically than what I was saying. Visually, I was saying, oh, if it doesn't have this and this and it's all clean. But algebraically, technically, the fact that this is degree 1, the highest exponent tells you the degree, and the degree tells you how many solutions to expect. Okay? So this is a degree 1, single variable linear. Or I can also put, that means degree 1, okay, which is because of the exponent, which is a 1. So you get one real number And I just mean it can be positive, negative, zero, fractions, decimals, real numbers. One, but that's in contrast to what we're about to look at. One real number solution. And what that means, again, terms, I'm setting up, sort of we said before, but I'm going to be comparing it to what we're looking at today as we expand on that, is 4. And may help you this vocabulary settle into 4 is the only value of x that satisfies the equation. Oops, that satisfies the equation. Meaning you plug in 4 to the original equation and you will get a true statement. And no other value, you can't plug in any other value for x and get a true statement. It will give you a false statement. 4 is the only thing that satisfies it or makes it true when you plug it in and test. Okay, so let's take that single variable linear equation and go ahead and solve it for 0. Meaning we're not solving it for x. We are moving everything over to the left so there's a 0 on the right, just like we did with the absolute value one before we graphed it. Okay. So we're using our addition property to make that happen, but we're not actually solving for x. So we moved everything left. So we are setting it equal to 0. And now let's say that y equals 0. So instead of 0, once we have it set equal to 0, we can go ahead and substitute y for 0. And then turn it around, just because it's easier for the eye to look at, 2x minus 8. So we went from this single variable linear equation to the related two variable equation. And we can go in both directions. If we have this this two variable equation and we can put this on a graph and it's going to make a line, and we want to know where that line crosses the x-axis, we want to know its x-intercept, what would we do with this equation?
Graph it.
You can graph it and see it visually, but without a graph, how would you find the x-intercept?
It'd be a slope of like 2 over 1.
That's visually, but don't think graphing it. If I said, here's an equation that would be a line on a graph, without graphing it, tell me where it crosses the x-axis.
2, 0.
Something about 0.
Would you just make y 0?
Make y equals 0. Yeah. Plug in y, we're going in the other direction. All right? Y equals 0. This is the definition. Y equals 0, which is the very definition of the x-intercept. Okay. If I say define x-intercept, you say it is the point and the only point for a line where y equals 0. So if you have a two-variable equation, and you know, hey, that's linear. If I put it on a graph, it would be a line. But without even looking at that, I want to know where does this line cross the x-axis. All I have to do is put in y equals 0. And when I put in y equals 0, I get that. Okay. And then I would solve for x, which takes me back to that. And I say, oh, this line crosses the x-axis at 4. At specifically the point 4, 0. It's an ordered pair. Okay. So that is all we're doing here. This is the related two variable. Here, once it's in this form, y could be anything. If we make y equal to 0, then we're finding that one very special point. But when we turn it into its related two variable equation, make it equal to 0 and then just substitute y, now y could be anything. Plug in an x, get a y. Plug in a different x, get a different y. Plug in an x. How many different x's can I plug in?
Infinite.
Yeah, and get infinite y's. How many points are on a line? Infinite, yeah. Okay. So once you have a y in here, when it's specifically y is 0, then you have that one special point. When you change it back in the related two variable, oh, you've got infinite points. That's what makes the line. All you need is 2 to graph it, but it actually has infinite points. Okay. Okay, so so let's make a table of values, which is the most tedious and least efficient way to graph. But it illustrates some important points about not just the linear family, but any family of equations or functions you would graph. Okay? So I'm going to make kind of a more extensive table. I'm saying basically that if x is equal to something, we're going to plug it in. The equation becomes the rule. And this is going to be a big topic of Thursday, that idea of a rule. Okay? A rule that's going to relate an x to a y. And that's where we start to define what a function is. And that equation forms that rule. So if x equals 0, x equals whatever, then you plug you plug x into the rule, and that means that it's going to spit out a y. Then y equals that. Okay. And you can choose anything you want for x, anything, because there's infinite possibilities. Okay. As we're going to look more on Thursday as well too, it's what's called domain. Domain is just what x's can you use, and for a line, there's no restrictions. The domain is unrestricted. That means x can be anything. Other families have restricted domains. Okay? In algebra, you'll learn how do you decide what that domain is. Okay? But for a line, your table of values can include anything. I'm going to go ahead and use these just so we'll be all consistent together. -1, 0, 2, and 4. Now, just like I was pointing out before, anytime you're plugging something in, whether you're checking the solution of an equation, or in this case in a table of values, always plug things in parentheses. Okay? It keeps fractions and negative numbers more clear. So if x equals -1, then y equals 2 times -1 minus 8. Okay? And then you see y. Okay? And then write that as an ordered pair. Okay? So finish filling out these values.
Well, like basically, that's what I was saying with the y on the top. We could have easily just found out like what x is, and then if it equals 0, then like,
oh, right.
Because 2
Yeah.
times 4 equals 8 minus 8 equals
Yeah.
0.
Oh, so that's when you can you can solve by inspection, because you can see, oh, how would I get rid of this 8 if this equals 8? Yeah.
And that gives you,
Yeah.
if y equals 0, then that's your...
Exactly. That's kind of a way of doing it backwards. When you're involving fractions and other things, sometimes it can be more complex. Yeah. So the definition is set that equal to 0 and then solve. But yes, some of them you can absolutely do mentally the more you get used to looking at it. Yeah. I see what you're saying. Yeah. Now, when we plugged in x equals 4 into this equation, when x equals 4, what do we know y is going to be?
8. I mean 0.
Yeah.
It just takes it.
Yeah. Because when we solved the single variable version, we got 4. We know that's the x-intercept. And we know the definition of an x-intercept is when y equals 0. Okay? So if x is 4, then y has to be 0. Now again, how many points, I mean, I chose these 4 points, but how many different x's could I choose? It's unlimited. It's unrestricted. You can choose any x you want. And so you choose an x, plug it in, spit out a y. And keep doing that again and again and again as often as you want. You can even plug in y's and figure out what x is. Huh? And you will end up with infinite solutions. And those solutions are ordered pairs. And I'm contrasting that to what I put up here. The single variable linear equation gives you one real number solution. You get a number, 4, in this case. Okay? For a single variable equation, you get a number, a real number solution. For it's related to a variable equation, your solutions, you get infinite of them to begin with, And they're in the form of ordered pairs. They're not, excuse me, they're not single real numbers, they are ordered pairs. Okay? So y depends on what x is. You're going to hear this come up on Thursday too. Y is what's called the dependent variable because it depends on what x is. If x is something, then y is that. X is independent, plug in any x you want, and y depends on what you plugged in for x. And you can do that again and again and again, and all your solutions will come out as ordered pairs. These are numbers that are related. Anytime x is -1 in this particular equation, then y must be -10. They are related. They are glued together by this rule. Okay? And that's a kind of an introduction of what the functions are that we're going to look at on Thursday. Okay, so, let's see. So knowing if something is a solution visually, so what I'd like you to do is, everybody got a piece of graph paper? Go ahead, and I'm going to put it up on the Desmos up here, but go ahead and plot these points.
On one of the graphs?
Yes, just on the top left graph, yeah. Oh, and I forgot to mention, but let me, if you are, it is part of 8.1, but I don't cover it in class and I don't put it on the homework. But if you're at all shaky with the coordinate graph, graphing xy pairs, or where the origin of the quadrants and the axes are, that's all part of the first section of 8.1. Okay, so if you're a little shaky on ordered pairs, I'm happy to answer questions and work with you also like outside of class as well, but make sure you are comfortable with that. And 8.1 does cover it even though I didn't include it in the homework. Okay. So anytime you're like, I think that's review, but I didn't get that, then please, you got to reach out. You got to let me know so I can give you resources or work with you and get you caught up. But you got to let me know. Okay, 0, -8, and 2, -4, 2, and 4, 0. 0. Okay. So, infinite possibilities of what we could choose for x, but when we chose these x's and applied the rule of the equation to them, it spit out these y's. Those x's and y's are related. They form an ordered pair, and when you plot those ordered pairs, what do you get? A line, right. And because these aren't just random, what's called discrete ordered pairs, but rather they are part of the rule, y equals 2x minus 8, 8, then they're just 4 of the infinite ordered pairs that exist on that line with that name. So we would call these particular 4 and an infinite other choices solutions to this equation. These ordered pairs satisfy this equation. Just like the number 4 was the only x that satisfied that single variable equation, these ordered pairs are 4 of the infinite ordered pairs that satisfy this 2-variable equation. So if they satisfy it, that means if you plug in that x, it will spit out that y. If I plug in 4, 2 times 4 is 8, minus 8 is 0. It spits out that y. If I plug in 2, 2 times 2 is 4, minus 8 is -4. It spits out a -4. Okay? They satisfy this equation. You plug them both in, and it makes a true statement. That means it satisfies it. And visually, it means they're on the line. So you've got infinite other points that are not on the line. What would happen if you chose another point and plugged it in here? Would it make a true or a false statement?
It just depends if it's on the line.
Right, yeah. So if I chose a point, like here, -4, -6, yeah, I could plug it in here and it would make a false statement. If I plugged in -4 for x and -6 for y, I would end up with something that was false. Okay? Because -4, -6 does not satisfy that equation. It's a point on the graph, but it's not a point on the graph of this line. Okay? So it's not a solution. A solution visually falls on the graph. And algebraically, you can plug it in, and it satisfies. It gives a true statement. So it's two ways to think about it. Okay. So if you were asked to find if something is a solution, let me go back to. And I'm showing a linear example here, but this is true for any family. Okay. If you've got an equation, a function that has an x and a y in it, and you're asked, hey, all of those, no matter what the family is, absolute value, quadratic, linear, whatever the family is, that is a graph, whatever shape it is, that is made up of infinite points. Okay? And so any xy pair that falls on that graph is a solution, and you can plug in the x and the y and see, no matter what family it belongs to. So if we're working still with this family, the linear family with this particular equation, y equals 2x minus 8, ask is 1, negative 6, a solution? And also ask is negative 2, negative 8, a solution? Okay. Now I see some people make this a little more complicated than it has to be by like trying to plug in just the y and then just the x and do them separately. Okay. But remember, if this is a solution, what does it mean visually? This point is on the line. Okay? So that means that these two things are true at the same time. This x and this y form a pair that's on the line. So you can plug them in one time at the same time. Okay? Plug them in, make sure they're in the correct order. The y comes first here and the x here, so make sure you're plugging in things in the correct place. This is an x comma y. And always plug things in parentheses. And it's easier to drop the parentheses than to lose track with negatives and fractions if you're dealing with. So this would be y is negative 6 is equal to 2 times 1 minus 8. And I put a question mark because I don't know. Okay? That's the whole point. I'm testing it. Okay? If it is a solution, visually it'll fall on the line, but if I'm not being visual, I want to see if it satisfies the equation. And satisfying means you can plug it in, not just one number like with a single variable equation, but both numbers at the same time. And if it's true, it satisfies. We've got negative 6 equals 2 minus 8. Negative 6 is equal to negative 6. That makes a true statement. That true is not the answer. True means that this is a solution. And if you, let me go back to, so on our graph of y equals 2x minus 8, we had negative 1, negative 10, 0, negative 8, and 2, negative 4, and 4, 0. Let me make a point right now while I'm doing this, that when you draw your graphs, and hand graphing is a little different than what you're doing on my math lab with the computer graphing. So when I do post that extra practice, do make sure you do some of them, and because what you're going to see on my test is hand graphing. Okay, so even though you're going to get more practice on my math lab, I will give you some hand practice so that you're really comfortable with what you're doing that you're going to see on my exam. Okay? And so you want to make sure you draw edge to edge with a straight edge and with arrows on either end that show it's infinite, it goes on forever. Not having arrows changes the meaning of the graph. And so we were testing the point 1, negative 6. So 1, negative 6 is right there. It falls on the graph. 1, negative 6. So it is a solution. Visually it's a solution, and it also made a true statement. All right, so test the second one about 2, negative 8. You can check it visually and also plug it in and see what kind of statement it makes. And the big thing here is just making sure you're plugging it in the right place, no matter what order the x's and y's are in. They're not always in this pretty form. Okay?